First of all, I would like to thank Mark for the invitation. It's very great pleasure to visit CERN every time. And so today I'm talking about the unique equilibrium state for geodesic flow over manifolds without focal points. And some of you might find this thing very similar if you attend the conference last year in Edinburgh. That's indeed very true, because last year I was talking about surfaces, the unique equilibrium state of surfaces without focal points. So this year we are able to upgrade from surface to manifolds. So we become a higher dimensional person instead of just two-dimensional. Anyways, so this work is a joint work with Dong Chen and the Kehoe Park. Kehoe is also here, is over there, that handsome guy. Okay, so anyways, so the outline is like this. So the goal is so the general overall goal of this project is try to deal things with from uniformly hyperbolic to non-uniformly hyperbolic systems. So we want to study the properties of equilibrium states, especially the uniqueness and the sub-ergodic properties of these measures. And I will go over quite a few earlier results. And especially it's starting from Knieper's 1998 seminar paper on annals, then Gelfer, Rogiro, and this four wonderful person produced a very nice work. And I will also introduce some terminologies and the pictures so that we can really understand how this method invented in here applied to our setup and the strategy of the proof. And it will really based on the Copenhagen-Thompson criterion. It is a very handy method, help us to really figure out if the equilibrium state is unique or not. And to do this, we need a very essential quantifier to define hyperbolicity. And I will discuss much more detail about this number in the end of the talk. Okay. Then, so the goal is from uniformly hyperbolic to non-uniformly. And this is the perfect world. And we hope everything happening here happen again. But the realistic world and the perfect world is always have some difference. But anyways, so here's for example, we take M is a compact negative curve, the manifold, and the Ft is a geodesic flow over M. Then we look at the Hurter continuous potentials. You always have these very nice properties. The first one is, yes, unique equilibrium state. And I will tell you every definition of every terms I wrote in here. Oops.
Welcome to the real world.
Yeah, come back. Okay. And yeah, so first one, what is the topological pressure? And here we can define a very neat way by using the variance principle. So it will be the measured theoretical entropy plus the integration over that measure, and mu is a flow invariant probability measure. And equilibrium state is the measure which realizes the equality in here. And still the same picture, the same thing. Okay, then Bernoulli. Bernoulli is more like the best mixing properties we might hope for. So in this setup, we will have the measure corresponding to this potential is Bernoulli, which means the geodesic flow is isomorphic to a Bernoulli flow, which will imply mixing in all orders. So that is really strong condition we hope to get. And a measure is a weak star limit of the weighted periodic orbits. That means you can just weight this. You just put the rock measure on every closed orbit and do the average. And this measure, when you take weight star the limit, it will converge to this equilibrium state. And it's real analytical, just like the picture look like this. So you put a quantifier, you put a scatter in front of your function phi, and you perturb phi, and you can just get the graph like this. So this is something we really try to see if we can get all these things in the non-uniformly hyperbolic setup. So it's the general questions, like how much things we can really recover from here. Okay, so in general, for a uniform, non-uniform hyperbolic setting, there are I would say there's two main types. One is the manifold is not compact, which will reflect to the topics Professor Poland mentioned this morning. It's just like your surface is not compact. Then things you need to taking care in different way. And there's a lot of things you can do, and which is you can really take a look at the wonderful book written by Poland, Polika, Shapira. It's very nice detailed way to really taking care of this equilibrium state from a Patterson-Sullivan approach. And another case, when your surface is like constant curvature, you can still using, especially for surfaces, there's still some coding method you can apply. So you can still play some game of the symbolic dynamics. Then in that perspective, using this countable alphabet symbolic dynamical system, you can still construct the equilibrium state and then get some ergodic property from there. So this is the first type. However, this is not the type we are going to concentrate today, but it's still a very interesting topic. The thing we are going to emphasize today is non-uniformly contraction and expansion. So for example, it's like you have a surface or manifold, you have some flat part. So it's not always contraction. You contract, when you enter the flat part, it stops contracting or expanding. So it is not, some region is like the behavior is a little bit different. So the first example is manifold without non-positive curve manifolds. So it's like manifolds with some flat region. So these are results on this setup. And I will give you more information later on. And another one is surface without focal points. And there's Galfer, Rogiro's paper, and Dong, Kehoe, and I, we have some work on this topic as well. And surface without conjugate points. So there's a Kermenhega, oops. Why? Kermenhega, Thompson, Kermenhega, no Thompson, I'm just so into Thompson. Kermenhega, Knieper, I can help myself. Kermenhega, Knieper, and a wall. It has something for surface without conjugate point. So it's very nice result, a very recent result. And in here, I mentioned so many like hierarchy of manifolds or surfaces. So here you need to mention it, you do keep in mind here, as well as there's also results of Liu, Wang, and Wu in 2018 about a manifold without focal point. In here, only thing you wanted to keep in mind is there are different hierarchy. If you are a non-positively curved, then you have no focal point. If you have no focal point, then you have no conjugate point. So it's this group is the biggest one. This set is the biggest one. So it's like different scale and different generalities. And we will talk about more detail and more definitions, but in this slides, you just need to keep this in mind. Just like a lot of different people that are doing different things in different scale. And the more detail will be in here. So this picture is an example of like surface of non-positive curved surface. So you have some flat region in here, and the other parts are negative curved. So this is one picture. And I definitely steal this picture from Vaughn's slides, I think. Anyway, a lot of pictures of my talk is just steal from so many people. I will try to credit them as long as I remember. Okay, so the first seminar result is from Knieper. He proved the uniqueness of the measure of maximum entropy, which we will just call MME, which means it's with respect to the zero potential. And after, it's 2018. Yeah, 18, right? So it's a very nice work from BCFD, which stands for Kisburn, Kermenhega, Fisher, and Thompson. They have a result of the uniqueness of equilibrium state for a large class of potentials. So it's definitely including these zero potentials. So they can take care of much bigger functions. And for surfaces, Galfer and Rogiro has a similar result like Knieper's. They have proved the uniqueness of the equilibrium state for the MME. And Don, Kehoe, and I, we proved for potentials. And if you read carefully, we put a large in here. There's no large. So they definitely, in this paper, they definitely taking care of more functions than us. But we still cover this uniqueness of AME in this paper. And for manifold without focal points, and Liu and Wagner, they also prove the uniqueness of MME. And today we are going to present a result of uniqueness of equilibrium state for a large class of potentials. So it's just pretty much the same class of this work. And you might feel, okay, so for these two works, Knieper's work and Liu, Wang, and Wu, their work, they mostly follow the same approach from Patterson-Sullivan argument. And Gelfand and Rogiro, they are super smart. They are using very different approach to this problem. So they are quotient out the non-expansive part. So if for a surface, so that you can do this thing for a surface and for without focal point, because there's something called a flat strip theorem. So if you are a singular set, then it's pretty much a flat region. So you can really clap that flat region to a geodesic. And after they do this kind of like surgery thing, so the end up manifold they get is like you can find the flow on that surface, the new surface is the hyperbolic flow. So you can play the old game from whatever you know from the hyperbolic flow to this setup. So it's very different approach from Patterson-Sullivan approach or this approach we take. In these three work, BCFT and our approach, it's really using Kerman-Haga and Thompson criterion. So you might feel like, you will see if you got a chance to look at our paper, we really pretty much try to mimic everything done in this BCFT paper. Okay, so the results. The setup is here. M is a closed rank 1 manifold without focal points. There are so many missing terminologies, and I will define them right away after take a look at the results. And so the first one is, if your function phi is a Holder continuous function with this property called a pressure gap, then this function phi has a unique equilibrium state. Okay, so this is just for uniqueness. And this is the singular set. I mentioned singular set so many times. I will give you the precise definition later. But you can understand this by definition is vectors with rank bigger than 1. It's the rank in here is different from the rank you learn in the Lie algebra. It's different rank. So it's Riemannian geometry rank. And in particular, if you look at surfaces, a vector inside a singular, so this is a vector in the unitangent bundle of the manifold, or surface in this case. A vector is inside your singular set if and only if the Gaussian curvature of the footprint of that vector is equal to 0, especially along the flow. Always equal to 0. That means this vector is sort of trapped in the flat region. And we call this vector is a singular vector. So you can see singular is sort of vector will live in a very flat region. Okay, then theorem B is more about the ergodic properties of this measure. And from here, we can get this measure is fully supported. And it is full measure in the regular region. So regular region is just the complement of the singular set. Okay, then it's chromograph. And this K means it's a stronger mixing property, and it can be understood as it has, for any non-trivial partitions, it has positive entropy. So it's very strong. It's less stronger than Bernoulli, but stronger than mixing. And also we will have the weak limit of periodic orbits, weak star limit of periodic orbits, especially on regular orbits. So you don't need to read average over every orbit. You just need to take care of the regular orbit. The regular orbits means the vector is generated by some vector inside the regular set. Okay, so you can see we are getting close to the perfect world. Okay, this is B. And then this means also what I mean by the taking average. Okay, then pressure gap. So this is an independent question, like how you get the unique equilibrium state is different. It's not that close to how you get a pressure gap. So it's different estimates you need to work on in here. And in our previous paper, we didn't work out this part, I think, because we are not ambitious enough. But because will be on the job market, so I become more ambitious by the time. So we are able to do this right now. And so there's a right away corollary that we will get a uniqueness of the measure of maximum entropy. So this contains the zero potential. Okay, so that will sum up like we will really cover the previous results. And this is not a very advanced pressure gap property. It's just really, you just take a super and inf, and you will play by the definition of the pressure. You will get this inequality right away. However, these two are all kept by perturbation. So that means you can do a C1 perturbation, then you will still have these two theorems. You get a perturbation as long as you still keep the pressure gap. And because pressure is continuous, so you will still get these two type of the pressure gap condition. So you can see the theorem tells, so how do we able to get the uniqueness of equilibrium state? You need to start from some potentials with pressure gap. And then the pressure need to have some regularity that you can argue it is unique. Okay, then for surface case, we can say a little bit more because mainly just difference is like geometric potential. In a higher dimension case, we're still not able to really handle the geometric potential. It's still much nuttier than we think. So it's still, hopefully we can deal with that after 2 weeks because we'll meet Keith Burns, who will help us, I think, hopefully. But anyways, so this is for geometric potential. So its definition is like this. So you are taking the derivative of your flow and restrict on the unstable bundle. Okay, then for this potential, we are not sure if, I think it's still open to see if this number is Herder or not. So in general, we are not able to really prove that it is Herder, but we still managed to really able to prove the uniqueness of equilibrium state. And moreover, for the measures we get in here, not only this geometric potential, but also the Herder potentials. All these equilibrium states corresponding to these potentials, they are Bernoulli. They are not just Kolmogorov. They are more stronger. They are Bernoulli. But that's only hold for the surface case. And moreover, in this case, it's also one place to show you the ideal world. The perfect world is different from the real world. So in here, the geometric potential, you put a Q in here, the pictures look like this. So there's a phase transition. So it's not real analytic like that. You will hit some wall and you won't able to say anything more. That is a sharp bound 1 in here. Okay, so that is something we want to discuss today. And then there's still a lot of missing terms I'm going to need to define. So here will be the preliminaries, like so many terminologies we need to define to go over the result again in the end. Okay, so starting from Riemannian manifold without focal points, and what does that mean by rank 1, and what is the singular set and regular set. And that's everything showed up in the theorem. Okay, so first one, to understand what is a manifold without focal point, we need to start from Jacobi fields. And the Jacobi fields is a vector field satisfy this Riccati equation. Okay, so this R in here means the Riemannian curvature tensor. And no focal point means in here, for every Jacobi field, 0 in the initial point, we know the norm is strictly increasing. So this is by definition, we call this is the manifold without focal point. Okay, then you have 3 pictures showing like 3 different categories of manifolds. So the first one, you can feel like this one is convex, this one is increasing, and this one is just never intersect 0 again. So they represent 3 different types of manifolds corresponding to the hierarchy we mentioned it before. So this, whenever you have a Jacobi field like this, when it is convex, then we call this manifold is manifold of non-positive curved manifold. So, or for non-positively curved manifold, the Jacobi field will always be convex. That's this important. This condition is very. This property is very important in BCFT's paper. They're using this quite a lot. And for manifold without focal point, it only means your Jacobi field is increasing. Okay, so you lose the convexity, but you still carry a lot of similar properties from non-positive curved manifolds. And the last one is no conjugate point. So you can see no conjugate point is more, it's just not here. You just get harder to control them, the behavior. So that's why Kremenhega, Knipper, and the Wolf's paper is so valuable, because it's a very big gap. Okay, so, and this is hierarchy in here. And remember, this is street content. There are examples which has no conjugate point but has focal point, which has a focal point, which has no focal point but has some region with positive curvature. So it's definitely different, very different areas. You need to treat them a little bit differently. Okay, so that is for first condition. And we also need to introduce some more information. So first one we call stable Jacobi fields. So it's a Jacobi field. I denote S means like it's stable, which means it's forward time, it's bounded. And stable hollow sphere. So stable hollow sphere is defined this way. If you know the hollow sphere from the constant curvature hyperbolic manifold setup, it's exactly the same thing. So when you take in, this thing is pretty much the level set of the Boltzmann function. And you take in t goes to infinity, that guy will converge to a surface, the hypersurface. Then that surface is called a hollow sphere. And they are all related. So if we know the unit tangent bundle of the geodesic of the manifold, you can split it to stable Jacobi field and unstable Jacobi field. So it will correspond to that. So for the flow, it's three directions. One is flow direction, and one is the unstable bundle and the stable bundle. And that will correspond to the space of stable Jacobi field and the space of unstable Jacobi field. So because of this correspondence, so you can take a projection, and the unstable foliation will correspond to the unstable hollow sphere, and the stable version will correspond to the stable version. So they are very closely related, especially in the no conjugate point setup. So here is more or less a notation. So it's unstable when you go backward time. And here I didn't rewrite any, oops. Oh. Okay, look at this again. Nice pictures. This is not steal from anybody. I drew it. Okay. But I'm going to show a picture which is stolen from von Kremenhega's beamer. So this is the picture of the two-dimensional hollow sphere, stable and unstable. So this is flow direction. And this is stable hollow sphere. This is unstable for hollow sphere. Okay. And I will introduce them because it will correspond to us how do we find the hyperbolicity quantifier to do something we call decomposition. So keep in mind, this thing just will be useful in the end. And rank 1. So rank 1 means, rank of a vector means the dimension of the space of parallel Jacobi field. So it's a very different definition from the group perspective. Okay, a parallel Jacobi field means its derivative of the Jacobi field is equal to 0. And more or less is the picture like some Jacobi field like this. And just remind you, the rank is always bigger or equal to 1 because you can always take the flow direction itself will be one Jacobi field. So it's always bigger than 1. And rank 1 means there exists at least one rank 1 geodesic. There's at least one rank 1 vector. Or equivalently, you can think there's a geodesic which travels to the negative part. It will always trap in the zero curvature part. It will travel to somewhere of the negative part. Okay, especially more interesting for surfaces, this is a topological condition. If your genus bigger than 2, then you are always rank 1. And in here, rank 1 will give us the topological transitivity of the geodesic flow. Okay, so this is all about the rank. Then we will go to singular set, because they are the friends we want to understand more. Okay, so they are the vectors with rank 2. So that means vector like this form. Okay, or equivalently, these are the geodesics, they bound some flat strip. And this thing is only true for a manifold without focal point. So you need some flat strip theorem to guarantee this. So it's not getting for free, it's not true for any, like for surface without a conjugate point. So this is something special for the manifold without focal point. And this is holosphere, or we are saying the holosphere has higher tangency, like you will see a picture. And interestingly, for the surface case, you can say it's just for the Gaussian curvature of the footprint of the geodesic flow is always equal to 0 everywhere. And the pictures look like this. And you can see this is not still from somebody else. You know who. And this as well. So this means like this geodesic stay in the flat region. This is a singular vector. It always trapped in here. So you can see this vector, even though it might pass this flat region, but it still travel to the negative part. So we call this vector a regular vector. Okay. So a singular set means in that region, the vectors for his whole life is lacking of hyperbolicity. It's trapping in some flat region, maybe like Midwest in the US. I'm living in the Midwest, I can say that, I think. And the singular set itself is closed and then flow invariant. And the regular set is the complement of that singular set. Okay, or it is open and dense. All right, so take a look again. So we should know every definition right now. And here the pressure restrict, this notation means the pressure restrict in the singular set. Because it's a closed set, so you can restrict it in this one and do the whole argument again. So we want this pressure is truly smaller than the whole pressure. And that's, I don't know why I put this red, right? But just like only periodic regular orbits. And we have all these pressure gap conditions and the uniqueness conditions. Okay, all right, so for surfaces we have this. All right, all the properties I just recall again. Okay, so what is the strategy of the proof? So as I mentioned before, it's really using the Thompson-Copenhagen criterion. This is a very nice criterion help us to do pretty much every work. And it is really inspired by Bowen's argument. So it's like a more generalized version of Bowen's argument in the uniform hyperbolic system. So it's pretty much the expansivity specification Bowen property will imply the unique equilibrium state. And this is the theorem we are going to use. And there are a lot of definitions. I'm not going to really tell you what every definition means, but I will tell you how to using our assumptions to taking care of every of them. So this notation I won't define, but it means like the pressure of abstraction to the expansivity. So it sort of measure the pressure of non-expansive part. So this condition you might feel right away, you will be taken care by the pressure gap. And there's a decomposition, which is very important, and the specification, Bowen property. The most important thing is this G is just a good set. It's a good part. We are not asking these properties to hold everywhere. We're only asking it is true in this part. So it gives us a lot of freedom to really play with them. Okay, so this condition will be taking care of this pressure gap condition. And it's more or less you can think of in this part, in this geometry setup, because of the flat strip theorem, the non-expansive part is pretty much the flat region. So it will coincide with this non-expansive part. So it's taken care by the flat strip theorem. So this part is not that hard to verify. And the specification means a way to glue all orbits. So you give me a finite six segments, and then we have a uniform way to glue them together. And Bowen property, more or less, is a regularity property. We need, the function has a nice regularity to really play all of these games. And this part means, so we say the middle part is a good part, and the initial and the ending part is not that good, it's okay. But as long as the small part, these two parts, they have smaller pressure. And this part you will see, we are able to using this condition to overcome. This condition can also help us to get this one. So in other words, the really important thing is to get a decomposition. Then how do we do the decomposition? How we chop every orbit in systematic way into 3 parts. So that we need a very nice geometric decomposition. We need a quantifier. We need a number to tell us how to do this decomposition. And we will see right away. We see this good decomposition. You can have specification in this region. Because what I'm saying is like when you region a good part means you have nice hyperbolicity. When you have a nicer hyperbolicity, that means you have better contraction and expansion. So that sort of like means you have a better chance to glue them together. And this pressure, this condition will help us to really get through this condition. So in the end, I will give you a lot of pictures, tells you how we really verify all of them by using our questions. Yeah.
Do you know anything about the support of this equilibrium state?
The support of this equilibrium state is outside, is on the regular set. It's full measure on the regular set. Yes. Okay, then how do we do this? So still more terminology, so I need to tell you, this will be quick, just definitions. So decomposition, we need to chop our orbits into 3 parts. So you don't need to worry about these words. It just like tells you for every finite orbits, you can chop them into 3 parts. So the blue part is a good part. And this part, they can be bad. That's fine. Okay. Then this is called decomposition. So it more or less reflect to this picture. So these 2 parts, they are lying around this singular set. They are lying, not singular set, they are lying, staying in this flat region. And the blue part travel in a negative curved part. So it's the picture you can keep in mind. Okay, and we will need a quantifier to do this decomposition. Okay, specification just like what I just mentioned before. So you give me any finite segments, we can glue them in a uniform time. So every time, what's wrong with your specification? Oh, okay. So this picture. So the time, the gluing time, you have a uniform control. Okay. So for every segment, any segment, you give me epsilon, and then there's a finite fixed time tau. I can use in the time tau I smaller than that tau to glue all these orbits together. Okay. So this is called a specification property. Then Bowen property is very, just like if you have 2 vectors stay in one Bowen ball, then I'm asking their integration won't be too far away. So this is a Bowen property. So you can see if you have Hurd continuity, then you can recover this Bowen property very quickly. And we are only asking this property in this good set. So I'm not asking you to have this property everywhere. For example, it's not going to be true in the singular set, because in the singular set, you can be far away, and you won't be able to really control if your function has different value in the singular set. Okay, and the quantifier, so in here, I took the surfaces case as the baby example because it's much easier to see, and it has much better geometric understanding. But that won't take us to a higher dimension. We need to upgrade ourselves a little bit. So this is a stable hollow sphere, and this is unstable hollow sphere. So we are, for no focal point, one can prove that these 2 spheres, hollow cycles, these 2 hollow cycles, they are convex at the C2. Because it's C2, therefore, you can look at what is the curvature of this hollow sphere. So we are using the curvature and integrate this curvature a little bit more. So this, for any vector v, I integrate the hollow, so you move front and move back a little bit, and using the integration of this number and taking a minimum. We're using this number as our hyperbolicity. So you might curious, like, then why we need to do something like this so strange? And in just one thing I want to mention, in the non-positive curved case, they don't need to take the integration. They only really look at this curvature. We will see in the next slides. So in taking integration is something really happen for no focal point, because the lacking of the hyperbolicity, we need to have more time. We need to accumulate more hyperbolicity so that this number is good enough for us to apply to our estimates. So we need take some longer time. So we need to integrate a little bit instead of just looking at that value. And so you integrate, you add extra time t and in the starting point and ending point. So you integrate some t. So this t is still a variable in here. And then we can determine this t by our pressure gap in the end. So we can find a t in the end. So right now it's just a variable. Help us to have some room to play. And yeah, this will be determined by the pressure gap condition. Okay, still the same. So this lemma, this lemma is easy lemma. If your vector is a singular vector, then this curvature is equal to 0. So that, remember, this is my curvature. This lambda t is equal to 0 for all singular vectors. Because remember, singular vectors is just like, it's a flat. Yeah, it's a paired Jacobi field. So that means these two guys, they're all equal to 0. Okay, so this red lemma is really the very important lemma we hope our number to have. For every hyperbolic indicator or quantifier, we hope they can really sort of characterize the singular set. So we need this lemma, which tells us that if for a vector v, this number, when you take a t, integrate very big, if this guy equal to 0 for all t, then this vector should stay in the singular set. So it's sort of like give you kind of this kind of picture. Singular set is a smaller set in the region. And I hope using this lambda to characterize the size of my singular set. So with this lemma, it tells us like, if your t go to big enough, then you are getting close to this singular set. Okay, so this is something we really need. And this is something we need to use in the no focal point setup. In the non-positive setup, you don't need to do this t thing. You can just using the lambda is good enough. Using the curvature is good enough. And in here, I was telling you, our proof in this setup for this lambda t, we need to use in dimensional 2 condition. So that's why we were not able to do a higher dimensional last year. So we need to, in other words, to do all this project, you need to figure out a nice geometric hyperbolic quantifier. So this thing is not going to work. So we are taking care of another one. So here are just some remarks. So for a non-positive curve manifold, they are using this lambda by this minimum of these two vectors, two numbers, not vector. So this means this is the smallest eigenvalue of second fundamental form of the hollow sphere, unstable hollow sphere, and this is the smallest eigenvalue for the stable hollow sphere. So it's these numbers, they are just curvatures if you look at surfaces. And that number help BCFT really do the decomposition. And for the surface of no focal point, we're using these two numbers. We sort of just integrate. We just sort of integrate this number. And but it's a little bit different in the higher rank, in higher dimensional case. We need to take care of this kind of number, and this kind of number will do the work. Okay, and it's a little bit odd, but in fact, first thing is for surfaces, because this Riccati equation, you can see these two numbers, they are exactly the same. Because in surface, you don't need to worry about this the vectors in the perp of this given vector, because it's just one dimensional, because you are living in the surfaces. So these two numbers are exactly the same number. And another thing is in the high dimensional, if you just take in integration of this lambda u and lambda s, it is not sufficient to get the previous lemma, which should help us to categorize the singular set. So it sort of like forces us to really come up with a new quantifiers, and somehow this quantifier works in this setup. It's not very hard to image. We really need to go back to the Jacobi fields, because Jacobi fields really govern the expansion and also related with the curvature. So it's not as geometrical as here, but it do the job. It does the job. So in this case, every argument is the same. Just replace this, replace the original lambda t by the blue lambda t by red lambda t. So it's really, this project is really the matter of searching a nice quantifier. Okay, so what is the decomposition? I've emphasized again and again, we need a decomposition to apply the Copenhagen-Thompson approach. So this is the decomposition. So this means the bad parts. So bad parts means it's lambda. You integrate the average of your hyperbolicity is smaller than eta. So give you a number eta. So this is orbits, a vector and a flow time for time t. So this is a finite segment. And if the for this finite segment, the average is smaller than eta, the average of hyperbolicity is smaller than eta, then we say this orbit is a bad part. This part is a bad part. And whereas the good part is the average is bigger than eta. So it's hard to understand by writing these things. You can take a look of the picture. So in here, this is eta. So this is the average. This blue red line means the average. So if the average everywhere is bigger than eta, so like this part everywhere is bigger than eta. So this part is some part we need to take in care. So this part is definitely in the bad part. And this is, you are not only look at the forward direction, you also look at the backward direction. So in here, this part will stay in the bad part. So the good part will be everywhere you chop the bad parts. So it's better, it's more important to identify the bad parts. Then the remaining part will be the good parts. So for every segment, every orbit, it will be separated into three components. Just like bad part, the first bad part and the good part and the remaining bad parts. Okay, so we are only asking every good properties to happen in the good part, like specification and Bowen properties. You need happen here, and you can see in here, stay in the good part. That means you have certain hyperbolicity, so you have certain contraction and expansion to play in here. So that's why this approach is more flexible. Okay, so the summary is this. So using geometry of manifolds without focal points and the pressure gap condition, we can construct a decomposition using the lambda t. And with this lambda t, we can prove it has specification property. And this is really coming from the geometry of no focal point. It's really coming from because the lambda t we choose and the behavior of the Jacobi field. And with this decomposition and this singular set, pressure gap condition, you can find a suitable time t. Just like we need to choose a suitable time t. Using these two conditions, you can find a time t. With this time t, we will see it later on. And with this, so these two conditions, so the geometry, in fact, in here, this implication is coming from the flat strip theorem, which is part of the geometry of the manifold without focal point. So using the flat strip theorem, you can really bound the non-expansive part by the singular part. So that's why you have this pressure gap will help you to still get a gap for here. So that is the first condition in the Copenhagen-Thompson criterion. So that's in there. And this with the suitable time t will give us this. So because this is a gap, so and we know if we take t big enough, the vector which is 0 for all lambda t will converge to a singular set. So when you take time t big enough, the bad part will sort of shrink, will go into the gap. So that this part, when t is big enough, this part this thing is the last condition of Copenhagen-Thompson's criterion. The first one, the first part and the last part, the pressure of that two parts should be smaller. So using this gap, and with that important lemma, we can really find some t so that this guy will stay inside the gap. So we can get this. And plus the Bowen property. Bowen property is more or less more like a standard argument. It's especially here we only treat Hölder potentials. Oh, what did I do? Okay, so we only taking care of Hölder potentials. So you just do the estimates by hands. However, there's something a little bit tricky. Just in the reality, try to prove the Hölder property, and try to get that red lemma. There's a paddling between the lambda t. So sometimes you choose this lambda t, that might give you the red lemma, but won't give you the Bowen property. Sometimes it's vice versa. So you sort of try to win the battle between these two, and somehow the lambda we choose help us to do this at the same time. And okay, standard argument. And for for surface case, for geometric potential, it's a completely different approach. It's just really taking care of the Riccati equation. And in the two-dimensional Riccati equation, it's just an ODE. So it's much easier to do the analysis for that equation. So that's why we can still analyze things for the Riccati equation to get a Bowen property for the surface case. But in higher dimensional, because the equation become more chaotic, so we are not able to really say the same thing. Okay, so then all these things, so with specification and every condition, specification, decomposition, and the pressure gap, then that we can apply the Copenhagen-Thompson criterion. Then you can get the results. And you can also do the equilibrium, the ergodic properties of this measure. Okay, so one thing to mention, to get K, in fact, it's really coming from Cole and Thompson's recent work. We done nothing to do with that. It's really coming from their paper. Okay, so in other words, in their paper, they showed that for the equilibrium state getting from creating this hyperbolicity lambda, for equilibrium state getting from that way, they can always get K property. So especially the first example is for manifold without non-positive curve manifolds, and also our works. It can also give us Kolmogov. And one thing to mention, so for the surface case I mentioned, we can get Bernoulli. That is also not what we did. It's just really coming from Roger P.A., Lima, and Sarik's work. So their work proved for a surface case, satisfy certain conditions, then you will get Bernoulli. Then we satisfy all that given condition. So we can get this property. And the pressure gap is really an independent question. I didn't really mention too much in here, but the rough idea is really try to approximate the singular orbits by regular orbits and try to do the estimates carefully. Then you can get a pressure gap. And that's it. 3 minutes left. Okay, thank you.